Alright, today's video is on Chapter 2, Section 7, Piecewise Functions. We're going to start by reviewing how to evaluate a function in function notation. So we're given two functions, f of x and g of x. For number 1, we want to evaluate f of 2. When we have f, that means I'm going to go to my f of x equation opposed to my g of x equation. And my f of x equation is a negative 3x plus 2. Now, since I want to find f of 2, that means I'm going to plug in 2 everywhere that I see x. So it's a negative 3 times 2 plus 2, negative 6 plus 2. We find that f of 2 is equal to a negative 4. So if we've got g of negative 2, the g tells me I'm going to go to my g of x equation, which is x squared minus x cubed, and then I'm going to plug in a negative 2 for each of the x's. So that becomes a negative 2 squared minus a negative 2 cubed. Make sure you're using parentheses when you substitute. A negative 2 times a negative 2 is a positive 4 minus a negative 2 to the third power is a negative 8. So that's minus a negative. So we have that g of negative 2 is equal to a positive 12. We're going to use that idea for our piecewise functions. In real life, functions are represented by a combination of equations, each corresponding to a part of the domain. Such functions are called piecewise functions. So for example, our new f of x is we've got 2x minus 1 when x is less than or equal to 1. Then you have 3x plus 1 when x is greater than 1. So we've got two different equations depending on what our x value is. One equation gives the values when x is less than or equal to 1, and the other when it is greater than 1. So we've got to take that into consideration when we evaluate that piecewise function. So the first one that we want to evaluate is when x is 0. I have to start by looking at the domain. So we want to see, is 0 less than or equal to 1, or 0 greater than or equal to 1? It's not greater than 1, it's less than or equal to 1. So therefore, I know that I'm going to have to substitute x into the equation that corresponds to that domain, which is when f of x is 2x minus 1, because 0 is less than or equal to 1. If I want to evaluate when x is 5, we've got to do the same thing. We've got to look at the domain. So is 5 less than or equal to 1, or is 5 greater than 1? Well, 5 is greater than 1. Therefore, I'm going to plug 5 into 3x plus 1 because 5 is greater than 1. And last, if I want to evaluate when x is equal to 1, so 1 is less than or equal to 1, 1 is greater than 1. The one that is actually equal to 1 would be our first equation, so we would plug 1 into 2x minus 1 because 1 is less than or equal to 1. So you have to figure out, where does that number go? You have to look at the domain to determine which equation to plug it into. So just again, when you are evaluating a piecewise function, you do not substitute the value into every single part. You don't plug it into every equation. You only plug it into the equation that satisfies the bounds. So now, beyond evaluating a piecewise function, we're going to graph a piecewise function. So we still have that same two equations, 2x minus 1 and 3x plus 1. For our certain bounds, we are going to look at the first piece of 2x minus 1. So right now we are concentrating on the first equation in our piecewise function. Find the boundary point. You know that y equals 2x minus 1 is going to represent the graph where x is less than or equal to 1. Now if I just wanted to graph this line, I would be at my y-intercept of negative 1, my slope of 2 over 1. So if I graphed the entire line, this would be representing my line. The thing is, I only want to represent the graph when x is less than or equal to 1. So here is when x is equal to 1. Because it's less than or equal to, I'm going to have that closed circle, but I want to ignore everything that has x values that are greater than or equal to, because my domain is less than or equal to 1. Or you can think about the fact of, we're going to find the value when x is 1. So we have 2 times x, which is 1, minus 1. 2 minus 1 is 1. Therefore, our first point is going to be at 1, 1. We plugged in a value of x was 1, and we took out a y value of 1. Again, showing us that first point. And then we wanted it when it was less than or equal to 1, so I'm going to move my graph to the left when my x values decrease. So again, we're going to start here at 1, 1, and we want to make sure that you have a closed circle because our domain is less than or equal to 1. Then draw your line using your slope for all values, following the domain, so we want our x values to get smaller. Now we're going to look at the second piece. The second piece of our equation is 3x plus 1 when x is greater than 1. So again, if you want to think about it one way, let's graph that line. We start at 1. Our slope is 3 over 1. So we go up 1, 2, 3, right 1. Up 3, right 1. Up 3, right 1. Down 1, 2, 3, left 1. Down 3, left 1, and so forth. So those are all the points on our second line. We want our x to be greater than 1. So we find out what the value is at 1, and it's 1, 4. But because it's a greater than symbol, we have to have an open circle indicating that it's not included. Then we want to follow the x values that are greater than 1. If I'm looking for x values to be greater than 1, I'm looking for my x values when it's 2, when it's 3, when it's 4, which means I'm looking at my line going this direction, and these points are not part of our graph. That's one way to do it. The second way to do it, again, is to look at the second piece, your boundary point. You know that it's 3x plus 1 is going to represent the graph when x is greater than 1. So we're going to plug in when x is 1. So we've got 3 times 1 plus 1. That gives us 3 plus 1, which is 4. So we had an x coordinate of 1. We found that our y coordinate is 4. So our starting point is going to be at 1, 4. And we're going to make sure that we have an open circle because our boundary said that it's greater than 1, not greater than or equal to 1. Then draw your line using your slope for all values where x is greater than 1. And we know that our slope is 3. So if we were to go back up to our graph, our starting point at 1, 4, we have an open circle, our slope of 3, and we want it when our x values are greater than 1. So we are looking when our x's are increasing, so we're moving to the right. Up 3, right 1. Up 3, right 1. So there are the two pieces to our piecewise function. To the left of and including x is 1, the graph is given by y equals 2x minus 1. To the right of 1, the graph is given by your second equation of 3x plus 1. And that is all determined by the domain. So the fact that we've got x is less than or equal to 1 and we've got that x is greater than 1. That is determining which part of the lines we use. The graph is composed of two rays. Notice that it still passes the vertical line test because you have a closed circle at 1, 1 and an open circle at 1, 4. So it kind of is deceiving because you may think, oh, it's going to fail the vertical line test because it's one line, but when you go to draw your line right here, it's not including that point. So when you draw the line, it's not actually going through that twice. It's only going to hit at one time. The open circle means that point's not really there. Okay. And our last piece is similar to a piecewise, but it's a step function. So we've got h of x, and we have all these pieces to h of x. Just like before when we separated it and we said it was like y equals 2x minus 1 and y equals 3x plus 1, This is the same thing as saying we've got y equals 1. Well, y equals 1, the graph of the function is composed of 4 horizontal line segments because we've got y equals 1, y equals 2, y equals 3, and y equals 4. So those are going to be 4 horizontal lines. The first line segment is h of x is equal to 1, which is a horizontal line at 1, which is the same as y equals 1. However, you only draw this segment according to the domain. So we've got a horizontal line at 1. That's the whole line at 1. We only want a piece of that line. So we're going to not draw that. We want it at -4. And because it says less than or equal to, we have a closed circle. So we want the horizontal line at 1 everywhere from a -4 to a -2. So we've got our closed circle at -4, and we have our open circle at -2. So we have a closed circle at -4, open circle at -2. And remember, those are determined by your boundaries. Now we look at the second line segment. That's a horizontal line at y equals 2. You only draw this segment according to its boundaries from a -2 to 0. Here you have a closed circle at the -2 circle because it's less than or equal to, and then you're going to have an open circle at 0 because it's just a less than sign. So we've got a horizontal line at 2. Remember, the whole thing would be represented by that, but we only want the one little piece of it. Closed circle above the -2, open circle above 0. You have 2 more pieces. I want you to press pause and see if you can complete the next 2 segments correctly. So press pause now. When you are done, go ahead and press play. Alright, for your third segment, you should have a horizontal line at y equals 3. You only draw this segment from your domain, which is 0 is less than or equal to x, which is less than 2. Here, according to your range, you're going to have a closed circle at 0, and you're going to have an open circle at 2. So horizontal line at 3, closed at 0, open at a +2, and we want everything in between there. Our last segment is going to be a horizontal line at y equals 4, and you only draw this according to the range from 2 is less than or equal to x, which is less than 4, meaning you have a closed circle at 2 and an open circle at 4. Let's go back up to our graph. Again, less than or equal to, being closed circle at 2, open circle at 4, and everything in between there. So again, your step function is you're having these horizontal line segments in between these ranges. They still are going to pass that vertical line test because when you draw your line, it's closed here, open there. There is not a second point there. Anytime that it's an open point, that point is not included in the line. And that is your piecewise and your stepwise functions for the day.